I would like to thank SPP for the opportunity to share about the PNRI activities in capacity building in the field of neutron and reactor physics. This presentation has 4 parts. I will give a brief introduction about neutrons, what we're doing in the Philippine context, or more specifically in the PNRI setting, and what are we producing, local outputs from the capacity building and how it is accepted in the international setting. I would also share about future plans and opportunities, which I hope would encourage collaboration with physicists. When I first encountered neutrons in high school, I thought that they were boring because they're neutral, unlike protons and electrons that have charge. It turns out that there's a whole branch of physics dedicated to it because it has interesting properties which make it attractive in a lot of applications in a wide field, in a lot of fields. So its neutral characteristic or its neutral charge actually makes it highly penetrating because it is not affected by the Coulomb field of the nucleus. It has a substructure, two down quarks and one up quark, which this defines how it decays when it is not bound in the nucleus. So when it is not bound in the nucleus, it is unstable and it decays with a half-life of about 10 minutes. It has a nuclear spin. It has practically zero electric dipole moment, but the standard model predicts that it may have. It's an ongoing investigation, that there might be a slight rearrangement of the charges in its substructure. Although it has zero electric dipole moment, it has a non-zero magnetic dipole moment, which makes it react in magnetic fields, which makes it an ideal probe for magnetic materials. Its mass is comparable to that of protons, which gives it good and interesting interactions with hydrogenous materials. This is a sample spectrum of neutrons in a given field. So when there is a neutron in a given field, it exists in different energies, and the energies are typically grouped into 3. We have the fast neutrons when we have more than 50 keV upwards. We have the epithermal from about 0.5 electron volt to 50 keV, and then the thermal neutrons, which are typically the neutrons with energies that have less than 0.5 electron volt. But in many applications, cold neutrons are also interesting. These are neutrons with energies that have less than 1 millielectron volt. So the neutron energy is adjusted so that its wavelength from the so that its wavelength will be comparable to the material that it is probing. And then for spallation sources, it is possible to produce neutrons with energies as high as 10 mega electron volt and higher. But as you can see, this energy range is still way below than the energy range that are studied by high energy physicists or by particle physicists. So just like electromagnetic waves, where the interactions are defined by the energy of the photons, it's somehow similar to neutrons because the dominant interaction would depend on the energy of the neutron. For cold neutron, for example, or for slow-moving neutrons, diffraction may occur. And for thermal to fast neutrons, these are the neutron energies which may cause fission. Elastic scattering may happen for all for neutrons of all energies. And then we have here capture and inelastic scattering according to these ranges. Now, neutron interactions are described by probabilities that are dependent on the target material and the incident neutron energy. We have here on this plot an example of how the interaction probability of neutrons vary depending on the target nuclei. But compared to photon, like an X-ray, a 100 keV X-ray, which has a very predictable interaction with different materials, we see that there is no simple pattern in the interaction probability with neutrons. In fact, 2 isotopes here, hydrogen 1, hydrogen 2, they are the same element but different isotopes, but the interaction probability with neutron is very different. So this is again, this is for the same neutron energy. Now, let's say we have the same material and the different neutron energies. Here we see that for increasing energy, the interaction probability becomes less. for a given material. This is a crowded slide, and I do not intend to discuss everything here, but just to give an idea that because of the interesting properties of neutrons, it has found so many applications in all these fields. In materials, material science and engineering can be used as a probe for the structure and dynamics of interesting materials. And then in the industry, mostly non-destructive testing, agriculture, smart farming with neutron detectors, particle physics. From the decay of neutrons, it's giving clues about the beyond standard model. The theories probably know more about this. Environment and geology. We have geochronology here. Of course, energy. That is where neutrons are most known for. Neutrons are important in fission reactors and also fusion reactors, in life science, medicine, and even in security and non-proliferation. You can easily Google these keywords and you'll find volumes of materials published in these topics. Okay, but where do we get neutrons? There are basically two sources, natural sources and artificial sources. Where do we find them in nature? When neutrons interact with the when cosmic rays interact with the Earth's atmosphere, it causes a nuclear reaction that produces neutrons. And we also find it in the soil because there are naturally occurring alpha particles. And when those alpha particles interact with the light nuclei in the soil, it results in an alpha N nuclear reaction, which produces neutrons. But these are very weak, so we don't normally find neutrons in nature. The biggest sources of neutrons are artificial, and that is where most of the applications in the previous slide can be done. And the biggest source of constant flux neutron is a nuclear reactor where neutron is produced from the fission reaction. And the accelerators or spallation sources, where an accelerated particle, usually proton, hits a heavy target, which results in a nuclear reaction that produces high intensity neutrons. Then we have small isotopic sources where we have, for example, californium-252, which spontaneously fissions, and that fission produces neutrons, and also AMBE, americium beryllium, or alpha N sources like plutonium beryllium, which has a similar mechanism to what is described here in this soil, in what's happening. So alpha N reaction. Now, what we have here? So I've talked about neutrons in different setting, but what can we do here in the local setting? So the history of neutrons in the Philippines is intimately tied with the history of the Philippine Research Reactor 1, because it is the first and only nuclear facility that was operated in the country so far. And here's a brief history of the facility. We had it as early as 1955. It was first operational in 1963, and it was operated successfully for 20 years from 1964 to 1984. However, it was shut down after upgrade due to several problems encountered, and the facility has been shut down since then. So there has been more than 30 years with no operating nuclear facility, which resulted in the decline of expertise in nuclear science and technology, especially in neutron and reactor physics. So PNRI mostly redirected the research study on photon studies and interaction of isotopes or application of isotopes. But these two fields, neutron reactor physics, really declined. And the answer to that, or to respond to this challenge, a lot of capacity building activities have been ongoing since around 2012. And one example of that is the use of isotopic neutron sources. So I would like to share that most of these capacity building activities were birthed out of a burden, challenge, or a constraint. For example, the challenge that there are practically no one who understands neutron in the 2011 era, except the late Dr. Saligan, who was the one who started all of this. So we have here californium-252 fission source, which were actually recycled from the radioactive waste management facility of PNRI. We have here a plutonium beryllium neutron source, which was during 2011 or 2014. It was initially unknown and uncharacterized, and no one knew what it was. It's just a neutron source. Then we have this americium beryllium neutron calibrator, which was formerly unutilized and uncharacterized. And the capacity building involving these isotopic sources includes experimental and computational studies that are performed to characterize the sources, to train personnel, and to determine further use of the sources. To train more students, the annual Neutron School was conceptualized also by Dr. Saligan, but continued by his mentees, like this guy here who's done a lot of work. Um, so that started in 2012 to 2016. It was changed the course on basic nuclear science in 2017 to 2019. Unfortunately, we were not able to offer it this year because of the pandemic. The main objective of this course is to build competence in students and expertise in lecturers in nuclear instrumentation, neutron interactions, neutron and gamma measurements, and radiation simulation. The neutron laboratory was also established from 2016 to 2018. It is established for neutron detector calibration and to provide a facility for students and researchers in performing neutron studies. And then we have the PRR1. So we go back to this. As I have mentioned in the previous slides, it has been an extended shutdown since 1988. And now we are establishing the PRR1 Subcritical Assembly for Training, Education, and Research, or SATR for short. And SATR also stands for the objectives of the facility. The facility is intended to support nuclear manpower development, accommodate local access to an operating nuclear facility, train reactor operators, users, and regulators, engage stakeholders in nuclear and reactor engineering, and repurpose resources of the historical PRR1 facility. So for me, that the last part or the last objective is the most important role of the PRR1 SATR. So what is the Pure One Satter? What is involved? We will be using the slightly irradiated Riga fuel. It is an available resource in the facility. If it is not used, it will become waste. But through the Satter facility, it will produce beneficial. It will have beneficial uses. This facility will have low absolute amount of nuclear fuel, less than 5 kilograms, with a total core loading. Any fuel configuration will be subcritical, which means it cannot sustain its own on its own. It cannot sustain nuclear fission reactions, so it is inherently safe. It also has zero power operation at ambient temperature and pressure. It has inherent safety features, and we always endeavor to comply to national regulations and international recommendations. For the utilization plan, according to its objectives, it will be used for public awareness, nuclear education, capacity building, and R&D and services. But we acknowledge the limitation of the facility, and we have full capability for utilization 1, medium capability for utilization 2 and 3, and low or demonstration capability at least for the fourth plan. We also have other externally funded research activities. This is also birthed out of a constraint because we don't have a spectrometer that is available in the Philippines before. So our team has proposed this project, and we were able to eventually develop a novel design because this is very different from conventional Bonner sphere spectrometer in terms of structure at least, but the mechanism is the same. So in terms of the structure, it's more portable, and it can be used in the field because it weighs less, and it can accommodate different detectors in different configurations. That spectrometer has already been deployed in a PET cyclotron facility and a medical accelerator facility by thesis students, Williard and Aixin, who have worked with us for the deployment of the instruments. The characterization of RSPR1 fuel configuration is supported by the International Atomic Energy Agency. Here, we investigate the different configurations of the fuel to ensure that any possible arrangement would result to a subcritical multiplication factor. It also involves radiation shielding to demonstrate that it is a safe facility in terms of radiation protection. Now, okay, so I've shared that we've been doing a lot of activities, but the question is that's still local. How will it fare in the international setting? I think since 2014, we've started joining local conferences, and it was only last year that we've started joining international conferences. And I'm glad to share with you that 29 here's at least the three that participated last year and this year. And I'm glad to share with you that last year it is the first time that our group joined the International Conference on Research Reactor, and our contribution won the one of the five best posters. And this was done by one of our thesis advisees, Joseph. His contribution won the best student contribution in the International Youth Nuclear Congress. We've also gradually published the results of our work, and I'm happy to share that we're gradually publishing in ISI papers. Okay. So for future plans and opportunities, the team is proposing the establishment of a multi-source neutron irradiator that will be utilized for the following applications. So this will utilize the sources that we've previously studied and characterized. So it's also like a recycling of sources. Instead of making them like waste, we find use for them. And for PR1 Satter, what are the future plans and opportunities? So the PRR1 Satter can provide local access to basic education, training, research and development in reactor physics and engineering. Again, we acknowledge its limitation. On the front end, that is the training of the operators and the users of Satter, we plan to complement the limitation by the IRL arrangement, or the Internet Reactor Laboratory for Distance Learning. We already have the agreement signed, and there's ongoing preparation of infrastructure. On the other end, so after the student is trained from Satter, we will take advantage of the ICER arrangement, the International Center based on Research Reactor, where you can find all the applications that was in that crowded slide. And there's an ongoing drafting now of the MOA with CARI for us to establish this linkage. There. Other so physics. Where can physicists come in? Our activities actually have a computational part where we do simulation of radiation sources, detectors, and fields. An example of that will be presented by Charlotte Balderas in 5EE4. We also do computational design of radiation detectors and facilities, and also detector simulation. On the experimental part, we perform neutron measurements, spectrometry, and dosimetry, experimental validation of computational models, and deployment of detectors and facilities. An example of that was presented by Aixin yesterday in 2C05. On the theoretical aspect, we were happy to have Jeffrey Tare with us, who's an NIP student, and he introduced us to the fractional differential equation. Neutron transport is mostly approximated by diffusion, by differential equations as a diffusion process. However, there are some media that is highly absorbing, which results in a subdiffusion process, or highly scattering, which results in super diffusion process. And from how Jeffrey introduced this to us, these processes are more accurately modeled by fractional differential equations. And he will be presenting initial results from his study in 3F06 this afternoon. There's also the application of artificial neural network to solve differential equations. This was the work of one of our thesis students that won the best student contribution in the IYNC. Others, we have facility design, development of policies, development of training programs, and regulation for radiation and nuclear facilities, and more. So in summary, neutrons have wide-ranging applications in various fields, and research reactors are the biggest sources of constant flux neutrons. There's also this question of facility or capacity. It's a chicken or egg question, and we're currently building both. We are doing capacity building while establishing facilities. And the approach that we're applying in the capacity building is to repurpose, rehabilitate, reestablish, and reutilize existing resources. Also, in spite of the limited resources and local constraints, somehow we are gradually able to produce outputs that are recognized a bit locally and internationally. And the ongoing capacity building is opening several opportunities that could help establish our niche in the field of neutron and reactor physics. Here are the references, and I would like to acknowledge our team, the Neutron Reactor Physics Group of Plenary, with some experts there. Thank you so much.
The title of my talk today is Plasma Science in the Philippines, Progress and Purpose, where we share our contributions to the field of plasma science and vacuum technology. One of the basic mechanisms of producing a gas discharge or plasma is through electron impact ionization. Basically, you have an electron accelerated at a certain discharge potential such that the potential is large enough to ionize an atom, let's say argon. If the kinetic energy is greater than the ionization energy of the atom, then there's a high probability that the electron will ionize the atom. Plasmas occur naturally, such as lightning or the aurora or solar flares, but our interest lies actually in laboratory plasmas and those found in the industry. Plasma has been used in different products, such as the light bulb, the neon sign, and the plasma TV. One major application of plasma, gas discharges, and even vacuum technology is in the manufacture of microelectronics. For those who are familiar with this process, you have a series of deposition, patterning, and etching until you get your desired product. And because of this technology, we are able to enjoy our mobile devices, our tablets, and even renewable energies such as the solar panels. Plasma is used to modify surfaces. This can be classified as physical or chemical. For the physical process, this is strongly dependent on the energy of your incident ion or atom. At the lower energy regime, if you look at the figure on your right, you are growing another layer of material which we call a deposition process. A slight increase in the incident energy, you are removing particles from the surface which leads to ablation or etching. As you further increase the incident energy, then you are removing clusters of particles which we call sputtering. And finally, at higher energies, the incident particle can penetrate the surface and become embedded, which leads to implantation. On the other hand, a chemical process induces chemical changes on the surface. For instance, if you are attaching functional groups on the surface, this is a functionalization process. If you want a more permanent effect on the surface, then you can graft the surface. And finally, you can also grow a thin layer of polymer on the surface, which is actually similar to a deposition process. In addition, you can actually control the particle energy distribution of your gas discharge, such as this one. And if in case you want to remove the high energy tail of your distribution, then you can accelerate the ions through extractors and produce monoenergetic ion beams. This is actually the principle used during ion implantation. Plasma research in the Philippines was initiated at the National Institute of Physics in UP Diliman through the establishment of the Plasma Physics Laboratory headed by Professor Henry Ramos. Through the years, the lab developed several plasma devices for different applications, and in 2007, the magnetized sheet plasma system was patented, and in 2014, the coating technology was commercialized. Through the years as well, the lab was able to train 11 PhD graduates, 50 MS graduates, and 50 BS graduates. The Plasma Physics Laboratory of NIP was one of the first laboratories to realize the transition from laboratory research to commercialization. So in this slide are two images of the sheet plasma device. On your left is the original plasma device housed at NIP, while the second image is the upgraded commercialized sheet plasma device for the coating technology. Prior to 2013, there were only two laboratories in the Philippines that work on Plasma and Vacuum Technology Research. These are the Plasma Physics Laboratory in UP Diliman and the Vacuum Coating Technology in Ateneo de Manila University. After 2013 and after several PhD graduates from UP Diliman, plasma laboratories were established at different universities around the country. For instance, at UP Baguio, they established the Plasma Physics Laboratory, while at UP Manila, a group uses plasma for biomedical research. At Fiat University, I believe they have their own atmospheric plasma system, while at the University of San Carlos, they are planning to establish their own plasma physics laboratory. In addition, Holy Angel University established its own plasma laboratory and started working on waste to energy research. A recent PhD graduate from Ateneo de Manila University is planning to establish his own plasma physics laboratory at the University of Science and Technology of Southern Philippines. Finally, I heard that MSU Marawi will have its own thin film deposition facility. Overall, these laboratories are working on different topics ranging from design of plasma systems to thin films to surface treatment and of course to for different applications. This is the Plasma Physics Laboratory at UP Baguio headed by Dr. Giovanni Malapit. This was funded by DOSC through an IDP grant. This is the Vacuum Coating Laboratory of Ateneo de Manila University. This is currently headed by Dr. Christian Mahinay. In UP Diliman, I believe we have two laboratories that are working on plasma and vacuum-based technologies, especially for thin films. One is at the Plasma Materials Interaction Laboratory, where I belong, and the other one is at the National Institute of Physics. In our laboratory, we try to design or modify our own plasma system, but of course, it depends on the availability of funds. So if we have funds, then we can ask our shop or a machine shop to fabricate components of our system. We then assemble, test, and then operate this for its intended application. So these are systems that we have restored or designed. So this is an old RF plasma system that we have restored. We have also developed an RF PECVD system where it has a remote plasma chamber. We have also built a DC plasma system using scrap materials from the lab. And we have restored a magnetron sputtering system for thin film deposition. This one is a low energy ion source system that we also developed in the laboratory. This one is a compact magnetron sputter type deposition system that we have recently assembled, and we will be using this for thin film experiments. We have also developed a cheap plasma device such as this one. This is actually a microwave oven that we converted as a plasma system. We have also initiated our work on atmospheric plasma systems. So this is a system that we have designed, funded by USAID, and we are using this for large area surface treatment. And then we're also developing a multi-target deposition system. So hopefully within the year, we'll be able to assemble this. Our plasma devices are designed for materials processing. So we can process different types of materials such as metals, ceramics, polymers, and so on. Our plasma devices and processes are used for changing the properties of the surface of any material, most notably the addition of a thin film for hard coating applications. We can also modify the surface and change its wettability. You can also use that for catalytic applications and so on. Researchers in plasma and vacuum technology established the Vacuum Society of the Philippines in 2015 to pursue and support research, development, and manpower training in the following fields related to vacuum, plasma, surface science, thin films, nanomaterial science, and technological applications. In 2016, VSP became a member of the umbrella organization IOVISTA, and also in the same year, VSP became an affiliate of ABS. Every 2 years, we also hold the International Symposium of the Vacuum Society of the Philippines. So first was in Ateneo, second one was in UP Diliman, and recently the third one was in Cebu. Because of our affiliation with the American Vacuum Society, we're given a special topic section of the Journal of Vacuum Science and Technology B for papers presented at the ISVSP. So as I've mentioned earlier, so the VSP is a member of IOVISTA, or International Union for Vacuum Science Technique and Applications. It has around 34 member societies around the world. We're also an affiliate of the American Vacuum Society. Most of our members are also active at the AAPPS, especially at the Division of Plasma Physics. We have also representation to the Asian African Association for Plasma Training, and more recently, VSP became a member of the Vacuum and Surface Sciences Conference of Asia and Australia. This map shows our collaboration with different foreign institutions. So this is how the plasma research will look like in the future, especially in the Philippines. So we will continue working on developing different plasma processes. This will be for thin film deposition as well as for surface treatment. At the same time, we will also continue designing our own cheaper versions of plasma devices. This can be classified as a vacuum system or can be operated in atmospheric conditions. And more importantly, we will continue looking for applications that are relevant here in the Philippines. For applications, we are looking at the manufacturing industry. We have an ongoing grant through the Cradle program, so we are still working on the coating technology. We will continue working with the tool and die industry. And then recently also, we have another Cradle grant, this time for the furniture industry. And then also, like Ateneo is working on optoelectronic thin films. We will also work on energy related projects such as development of photoanodes. We have an ongoing research project on vibrational energy harvester and also develop supercapacitors. We will definitely continue working on environmental applications, especially developing materials for the ionization, continue working on biodegradation of plasma-treated polymers, desalination membranes, and photocatalytic thin films. Then we are also looking at value-adding processes for natural materials such as cellulose, chitosan, zeolites, wood, and bamboo. And finally, we look at biological applications that includes biomedical, such as disinfection, sterilization, and wound healing, as well as for agriculture, that is for pre-sowing, growth, and post-harvest technologies. Hello. So I will end my presentation here. So finally, we have a clean room that we are developing. Hopefully, it will finish within this month. Thank you for your attention.